Hello class, this is the third module of this semester's Engineering Data Analysis. I have provided a study guide for this lesson, so you may check that for more examples. Just a quick overview of what we have discussed so far. Module 1 was Review to Descriptive Statistics. You learned about the terminologies, especially the terms population parameters and sample statistics. In Module 2, I discussed confidence interval estimations, which is an introduction to inferential statistics. It's a tool that provides a margin of error that lets us assume in confidence the population parameter is within an interval. Because of that, we can now safely infer from the sample statistic. In Module 3, which is this video, we're going to claim a value of a population parameter coming from a sample statistic. It's like confidence interval in a way, but in Module 2, an interval is solved, and then we're going to assume that the population parameter is in there. In Module 3, which is one sample hypothesis testing, we are going to hypothesize a value of the population parameter. We are going to draw some conclusions. We are going to infer on some scientific system. Now, what is hypothesis? Just a reminder, the plural is hypothesis with an E. So I will use that word a lot, especially when talking about the two hypotheses. Anyway, we famously know hypothesis as an educated guess. It is a statement predicting the relationship between variables. It is a foundation of scientific inquiry. Currently, you are second years or first maybe next year or in your fourth year, depending on your degree program, you will have a thesis. One of the most important part of your thesis is your hypothesis. You want to design a machine, it must be for a reason. You can say that your hypothesis is that your machine can improve a KPI. If you are a researcher, you always start with a question. You're challenging something. Hypothesis testing is about challenging the status quo. Now, hypothesis or HO is the status quo. Okay, it is of course important to declare what is currently the existing belief. Alternative hypothesis is your claim. This challenges the status quo. That means these two hypotheses are complements. Okay, let's have some examples for us to understand what hypothesis could be, and in every scenario, which one is the null hypothesis and the alternative hypothesis. For example, by some historical records, the company's probability of producing a defective product is 10%, and the new operations manager thinks the probability of defect is more than 10%. Your null hypothesis in this scenario is the probability of producing a defective product. Why? Because that is your historical record. So historical record is your status quo. It already has been recorded before, so that is what we believe. But the new operations manager wants to challenge that. But going back to the null hypothesis, the mathematical expression of that now is the probability is just equal to 10%. That is your null hypothesis. Now, by the challenge of the operations manager, they think the probability is actually more than 10%. So that is your alternative hypothesis, or your H1. The probability of producing a defective product is more than 10%. The mathematical expression of that is P is greater than 10%. Another example. A medical researcher wants to know if coffee drinking increases the risk of cancer in humans. So the null hypothesis there is the probability that coffee drinking causes cancer is 0%. So the mathematical expression of that is P is equal to 0. Your alternative hypothesis is what the medical researcher wants to figure out. That is it true that it's still 0%? What if it's not? What if there really is a risk of cancer in in consuming coffee? So The alternative hypothesis would be the probability that coffee drinking causes cancer is more than 0%. So your H1 or your alternative hypothesis will be P is greater than 0. Okay, so there is no existing belief that coffee drinking can actually cause cancer. We do not have an opinion of this. So there is a status quo belief that the probability is equal to 0, all because we never questioned it. Next, an engineer wants to know if there is a difference between the mean lengths of the bolts that were used back in the 2000s and the bolts the company is using today. The null hypothesis of that will be the bolts used now and then are not significantly different. So mu before is equal to the mu right now. The alternative hypothesis of that is what the engineer wants to know. The engineer doesn't think that it's the same, so that will be his alternative hypothesis. The bolts used now and then are significantly different. So H1 is mu before is not equal to the mu right now. So now let's summarize the differences between the null and alternative hypothesis, because you will figure out what is the alternative hypothesis in every worded problem. And of course, in the future, when you are going to create your own thesis, you're going to figure out what would be your alternative hypothesis. So null hypothesis is the expression that has been tested before, has been claimed in the past, or has been existing as a common knowledge. Alternative hypothesis is the expression that we want to see if true. Okay, it's the expression that we are speculating and the hypothesis we formulated ourselves. When you are creating the mathematical expression of the hypothesis, always remember that null hypothesis will always express equalities, and an alternative hypothesis will always express inequalities. So just notice the operators that are being used for alternative hypothesis. We don't have equal sign, while null hypothesis has them. So we could be using greater than or equal to, less than or equal to, or we could be using equal to only. Actually, a null hypothesis, even though the complement, diba? I've mentioned ganyan, they're complements. So if I'm using greater than for alternative hypothesis, that means I'll be using less than or equal to for the null hypothesis. Yes, we can do that, but since it's already understood that null hypothesis is the complement of alternative hypothesis, we can use the equal sign only. We don't have to really make them complement, make the operators complement. Okay, as long as alternative hypothesis is correct. Now remember, whenever you make a mathematical expression of the hypothesis, always use the population symbol. Why? Because these are the values that you are speculating. These are the values that you want to prove, and therefore are the symbols to be used in creating your hypothesis. We do not really have values for the population, right? Because they are only assumptions. Again, the focus of the subject statistics is that we only have the sample statistic, and it is uncertain that it is enough to conclude something out of that. That's why we have to put them through tools that could help us create probabilistic statements, making our conclusions more accurate. Well, the gist of that is your hypothesis statement should always have the population parameters as your symbols. Okay, I should never see x bars or p hats in your mathematical expressions of the hypothesis. Okay, it should always be population parameter. Now that I have clearly explained what hypotheses are, let's proceed to the hypothesis testing steps. I will explain them as we go. I'm going to explain as detailed as I could the theoretical concepts of each step before we proceed with an example, all right? So you can put hypothesis testing steps to heart. If you have any questions, you may comment below You may or may not place your name, but please mention your section. First step is to state the claim mathematically. It is important to know what your alternative hypothesis would be because that will be the basis of your next steps. In this example, the alternative hypothesis is that the probability is greater than 0%. Notice the operator carefully. It is greater than. That will be the basis of the variables for the next steps, right? So it is important that the alternative hypothesis is correct. The null hypothesis can be always equal sign, but you can also use the complement of the alternative hypothesis. And if your alternative hypothesis is greater than, then your null hypothesis would be less than or equal to. But again, it's okay to just put equal sign because it's understood anyway that the null is the complement of the alternative. Anyway, as long as your alternative hypothesis is correct, you can just put equal sign for null. By the way, if you want to learn the real relation between caffeine consumption and cancer risk, you may read the link I have provided. It is a review of related literature from papersdigest.com. Step 2, identify the level of significance, the type of test, and the sample size. Well, the sample size is given, and it is especially important if you're using t-test. So we won't deal with that for now. Let's focus on level of significance, which is symbolized by the Greek letter alpha. And let's also discuss about the tails of the test. To understand the level of significance, we have to understand the concept of errors. And to understand the tails of the test, we have to understand areas under the curve. All right, understanding the errors. Why do we need to consider errors in hypothesis testing? Because we are getting a sample from the population to test our hypothesis. And because of that, we will have some errors. We cannot be truly confident on the certainty of our study. We're always testing how true the null hypothesis is, and sometimes we could be wrong in concluding that because we are merely using a small pool of the sample. Now look at this table. If the null hypothesis is true and we happen to reject it, the error is called type 1 error, that is false positive. If the null hypothesis is false and we did not reject it, that error is called type 2 error, that is false negative. Going back to our coffee example, our null hypothesis is that coffee consumption is not related to any cancer risk, or the probability is equal to 0. If that is true, and we rejected it, then we are falsely saying that it causes cancer. If we concluded as such, we've made a false positive error, and it is a possibility to have such error, really. So we're going to integrate this error into our hypothesis testing. So type 1 error is also our level of significance, which is the alpha. So in some studies, we have to solve for the level of significance ourselves, but in default, especially in engineering studies, we use 5% as our level of significance. Now that connects to the tails of test. We're still in step 2, all right? These are sample diagrams. What are these shaded regions in the diagrams? Let me see if I could use the pointers there. What are these shaded regions? Remember the normal distribution and how statisticians develop a theory around it? It's what we call the empirical theory, right? That is the foundation of what we call the standardized scores. Standardized scores are on the x-axis. It could be a z-score or a t-score or a chi-square score. This represents the likelihood of the null hypothesis. If the standardized test statistic enters the small shaded regions, it means the null hypothesis is less likely. So we can reject the null hypothesis. Less likely. Look how small it is. It's just 5%. It's the error. Before that, how will we know where the shaded region is? Okay, because you will be the one to identify the tails of test actually. Okay, now go back to your alternative hypothesis. Okay, so these are the list of alternative hypotheses. Okay, we could have a greater than, a less than, or a not equal to. Identifying this is really simple, right? You just have to carefully read the problem. If your alternative hypothesis says greater than, then the probability of rejection is on the right side. We call that the right-tailed test. If your alternative hypothesis says less than, okay, the probability of the rejection is on the left side. We call that the left-tailed test. If your problem says there is difference, that means it's not equal. It doesn't matter if it's left or right. We're going to look at both sides of the equation, and that is what we call the two-tailed test. Why is this important to know? Because for the next step, okay, we're going to solve the critical value. Rather, we're just going to look for it in different tables. Okay, the critical value is different per tail, so we have to be accurate in identifying the tails of the test. In summary, for step 2, you will have to identify the 3 variables here. First is the level of significance, then the tails of the test, and then the sample size, which will be the basis of the degrees of freedom. We can elaborate about degrees of freedom later on for t-test examples. Step 3 is identifying the critical value based on 3 variables we identified from the last step. From step 1, you identify the parameters used, right? If it's an average, we use the z-test or the t-test. If the parameter is standard deviations, then it's a chi-square test. And if the parameter is a probability or a proportion, then it's a z-test on proportion. From step 2, you identified what table to use to finally find the critical value. And if you say the parameter is an average with large sample size, then it's a z-test, right? But z-test has 3 tables. Those 3 tables are right, left, and two-tailed. So that's why it's important because that tells us what table will we use to look for the critical value. All right, so if it's left-tailed, you will look at the left-tailed table. If it's right-tailed, you will look at the right-tailed table. So if you see here, the shaded region is on the left part of the distribution. So this is a left-tailed table, and the z-scores here are negatives. If it's two-tailed, then you will look at the two-tailed z-table. All right, let's say your table is two-tailed. Then your level of significance is 0.05. Then look at the 0.05 in this pool of numbers. Okay, where is the 0.05? It's right over here. There. So this is how you read, or this is how you search for the critical value in a z table. So 1.96 is your z-score. And all the pool of numbers inside, that's what we call the probabilities. These are the areas under the curve. Okay, there are other ways to look for critical value. It's not only looking for the probability and then checking the score. So I know that is quite tedious because there are so many numbers under the curve, right? So you can use Excel with the formula normsinf. I will provide the Excel template so you can explore this. You can use Google, so just look at the keywords that I provided here. Okay, but don't worry, for your exam, I will provide easy tables. You just have to know the variables in order to determine the critical value. And that's for step 3. Step 4 is simply determining the rejection region, and that is by drawing a visual diagram of it. How will you do that? Right, so it would look like that, of course. Going back to steps 2 and 3, in step 2, we will know where to draw our rejection region, right? So it's right over here. It will be on the right part. In step 3, we determine the score. And in this example, we use 1.645. So the probability of rejection starts at the z-score 1.645. And this shaded region, the area of that is 0.05. That's it. Those are the most important elements in drawing the rejection region. Make sure that you have the probability and you have the z-score. Going to step 5, which is calculating the standardized test statistic, we will know if the alternative hypothesis gets to be accepted or not. So you have to solve it using the formulas given. This is for z and t. This is for chi-square test, and this is for z-test on proportion. So you have to solve it using this formulas given. And it's simple. If you identify that the test is z-test on the mean, then use this formula. If it's z-test on proportion, then you use this formula. The value coming from this formula is what we call the z calculated or the t calculated or the chi-square calculated. Formally, in statistics, we call this the standardized test statistic. And whatever value you get, you will compare that to your critical value. Finally, the last step, based on all the steps that we did, we will conclude if we're going to reject or not reject the null hypothesis. If the standardized test statistic enters the rejection region, here, that means the null hypothesis is less likely. That means we will reject the null hypothesis. You can state the conclusion in this way. At 5% level of significance, there is a strong evidence to support the claim that the alternative hypothesis is true. If it does not enter the rejection region, then we do not reject the null hypothesis. You can state the conclusion this way. At something percent level of significance, there is no enough evidence to support the claim that the alternative hypothesis is true. These conclusions are stated in a strict probabilistic way, if you can notice. This is always our goal in inferential statistics. Notice that if I reject the null hypothesis, I can only say that there is enough evidence, there is strong evidence to agree that the alternative hypothesis is true. I can accept the alternative hypothesis. I can say that despite the smaller size, the sample statistics, okay, that one, okay, like the combination of the mean and the standard deviation or everything that you can solve from the sample, they are enough to conclude that my alternative hypothesis is correct. However, if I do not reject the null hypothesis, I can only state that there is no enough evidence to support the claim. Okay, why do I have to say it that way? Because not rejecting the null hypothesis does not mean I'm accepting it. You cannot accept a status quo because it's just arbitrary. Like, just because I do not reject the notion of the probability of coffee being cancerous does not mean coffee is really not cancerous. It just means I do not have enough evidence. It just means there hasn't been a study against it. Okay, it means it's based on my study only. There is no enough evidence. So another researcher can pick this study up and change the sample size or clear up the sampling technique. So that's why we can only state reject null hypothesis or do not reject null hypothesis. See hypothesis testing this way. You're not doing this to make sure you are right. You are a scientist. and you just want to find out if your speculation has any difference or your speculation has any evidence of being true. If you have any questions about the theoretical concepts of inferential statistics, you may ask questions down the comment section. Now that we're done with the concept, let's have an example. Pause the video to read the problem. All right, first, let's identify the parameter used here. According to this statement, mean lifespan, so the parameter is mean or average. It could be a z-test or a t-test, right? But then if you look here, the sample size is more than 30, so this is obviously a z-test. Step 1. State the claim mathematically. Let's identify which one is the alternative hypothesis first. The researcher made a study out of 100 samples to see if the mean lifespan is greater than 70. So the alternative hypothesis is mu greater than 70 because this is what you want to see if true. So let's put on both hypotheses. The null hypothesis is the opposite of that. So it's just mu is less than or equal to 70. We can just place equal sign. It's understandable anyway that the null is the complement of the alternative. And the alternative hypothesis is according to the statement, which is mu is greater than 70. So always look at the statement here, right after the operator. Now you might be wondering, how come 70 is the value that we put in the hypothesis? Well, aside from the obvious fact that it is the statement, this other mean, which is 71.8 years, is the sample statistic. We cannot use that. Okay, this is the value we found from observing the sample. The researcher got this from their calculations out of the 100 recorded deaths. Okay, this is not our speculation. This is not the population. Remember what I mentioned a while ago, the hypothesis will always be in populations. So another way to know what value to place with the hypothesis is that the value is beside an operator. It is said here, greater than 70. Greater than is your operator, so 70 is your population value. On to the next step, let's identify the three variables, which are the level of significance, which is 0.05 as according to the last statement of the problem. And then the type of test, it's right-tailed, because if you look at the alternative hypothesis, the operator used is greater than. Alright, so that means if your alternative hypothesis is greater than, the shade of the distribution is on the right side. And then sample size is, of course, 100. The next step would be identifying the critical value. So according to step 1, the type of test that we're going to use is z-test, right? And then it's also one-tailed because it's just right-tailed. So we're going to look at the right-tailed table or the one-tail interval, and we're going to look at 0.05. So it's right over here. That's 0.95 because again, confidence level is, I use that interchangeably with level of significance. They are complement. So if the level of significance is 5%, the confidence level is 95%. Anyway, so it's 0.95 and that means my critical value is 1.645. Next step is to determine the rejection region. So the rejection region is right at the right part of the distribution. The area under the curve will be 0.05, that is our, and then the z-score of that is 1.645. And then we're going to calculate the standardized test statistic. And since we are going to use the z-test on the mean, we're going to use the formula for, of course, the z-test on the mean. Right, so that formula is going to give us 2.02. So just notice the difference between the x bar and the mu. The mu is your population that is beside the operator greater than 70, so that will be 70. And then x bar is of course the mean on the sample, so that's 71.8. So I just want you to be careful about that because a sign is a difference. And then lastly, state the conclusion. So we know that 2.02 will enter the rejection region. So we can conclude that at 5% level of significance, there is strong evidence to support the claim that the mean lifespan is greater than 70 years.